Good morning. Welcome to the third week in our symposium. I'm very happy you could all join us today. We have four very exciting presentations today from some of the participants in the DesignLIFES network. And before we begin, though, I would like to take a few minutes to do a land acknowledgement. I think this is particularly important today, given that it is National Indigenous Peoples Day here in Canada. So I'd like to acknowledge that the City of Toronto takes its name from an Indigenous word, Toronto, which describes where there are trees standing in water. Where the University of Toronto is now located has been the territory of the Haudenosaunee Confederacy of Six Nations, and more recently is also the territory of Treaty 13 with the Mississaugas of the Credit, who are a part of the Anishinaabe Nation. Today, Toronto is still home to Indigenous, Inuit, and Métis people, and we'd like to acknowledge our thanks and acknowledgements to the people on whose territory we are able to live and thrive. Moreover, we pledge that in this acknowledgement, to turn our acknowledgement into action, to be partners with them in caring for the land and water. So as I said today, we have four presentations. As many of you are aware, the purpose of the DesignLIFE network is to train graduate students and early career researchers. So hopefully we'll have a slide coming up just showing our people. Thank you. So we have four speakers today. Sylvie Sprackman is a PhD candidate at the University of Toronto. Halim is a postdoctoral fellow, also at the University of Toronto. Taylor Hicks is a Master of Science student at St. Mary's University. And finally, Tamer Alamata is a PhD student at the University of Ryerson University. So first up today is Sylvie. So just give us a second and we'll have her load up her presentation. And I would like to remind everyone today, once again, that if you have questions, please put them into the Q&A form and I will be publishing them. If you see a question that you like, also give it a thumbs up, and we will have questions for each presenter after their presentation. So Sylvie, welcome to our online webinar.
Thanks so much for that introduction, Jen, and that was a really excellent land acknowledgement. If anyone joined late and you missed the land acknowledgement, it's too bad. I have to ask Jen to do it again. It was really great. Okay, so I'm going to be talking about some of my PhD research on the performance of mature bioretention. I'll start with a brief introduction of bioretention technology, but I'm pretty sure all the participants on this call understand it pretty well. So bioretention are designed to manage stormwater where it falls and trying to mimic the forested hydrologic state. So they're small, depressed areas containing engineered soil, media, and plants. This allows stormwater runoff to enter the system, then slowly percolate through the soil. And there may be underdrains if the native soil does not infiltrate quickly enough, and there's often an overflow system and organic matter and vegetation. In Ontario, the design goals for bioretention are often to retain 25 millimeters. This is equivalent to about 90% of rainfall events in Ontario. Have a minimum infiltration rate of 25 millimeters per hour, so we want that water to drain away pretty quickly, and a drawdown time of 24 to 48 hours, and this is to prevent standing water. Sorry, there. So in my research, I'm trying to answer these questions. You'll see in this presentation that I don't think I necessarily answer them all very well. We're getting there. And as I think all researchers say at the end of their presentations, there's more to be done. But what I'm trying to answer in this is, does bioretention last? Does it continue to perform its hydrologic function? Does it continue to improve water quality? And how do we know when it's failed? In deciding on the methodology for my study, I looked to past guidance from other researchers in the stormwater management field. So I'm going to recommend this methodology for others. It's from the University of Minnesota, and it's a book that's online and it's free. Practitioners, this is also like a really great tool. So I wanted to use a methodology that was both can be used in practice and has been used previously in the research. So the manual is called Stormwater Treatment, Assessment, and Maintenance. Pretty straightforward name. There's 4 levels of monitoring. level 1 being the least involved and level 4 being the most involved. And I did this at a variety of sites of mature bioretention sites in Southern Ontario. So the level 1 visual assessment involves checking if the inlets and outlets are free of debris and sediment buildup, looking for evidence of saturated soil conditions, which would mean it's not, that water is not draining away as it should. So that could be the soil color or the redox potential, the moisture content, or the most obvious one, standing water. You could also take soil samples and do some sort of basic analyses like particle size distribution, bulk density, or porosity, and checking the vegetation cover as well. So has the plant community changed over time? Are there bare patches? Questions like that. Level 2, a little bit more involved, capacity testing or infiltration testing. So you're looking to determine the saturated hydraulic conductivity of your bioretention media by taking a number of measurements, and there's a lot of literature to describe what kind of devices to use for this. In my case, I use the Guelph permeameter. Took about 5 to 15 measurements per site. You want to ensure you have like a breadth of coverage and to ensure high accuracy. And you'd want to repeat these tests under similar conditions. So antecedent dry days or the same time of year, because that can alter your hydraulic conductivity. The level 3 synthetic runoff testing, that is basically just dumping a huge amount of water on a bioretention cell, and then you get the sort of whole system infiltration rate and drawdown time. So this is a little bit more involved to do because your system needs to be able to be close to somewhere where you can dump a lot of water in an easy way. And some costs are involved, of course, in getting that water to your site. And then level 4, this is the continuous full-scale monitoring. This could be as simple as just installing water level loggers and checking those on a regular basis, or more involved, such as like water quality and flow monitoring for each storm event, shown in the picture here with the ISCO auto sampler. So this is sort of all the points of on this map show the different sites we assessed for inclusion in the mature bioretention study. I picked a cutoff of 3 years of age, a little bit arbitrary, sure. I decided on this from most bioretention research that's out there is on systems that are 2 years or younger. And so we had a lot of research on those systems already. So I was looking for something older, and that's how I decided on 3 years of age or older. I was able to find 30 sites in our network of partners from consulting firms and conservation authorities and municipalities. After checking them all out, went to 22 of those for the level 1 visual inspection, 19 of those for the infiltration testing, 3 of those sites for the synthetic runoff, and 1 of those sites, which is another part of my PhD anyways, for the level 4 monitoring. So again, speaking to the ease of them, like level 1 visual inspection, very easiest to do, and the level 3 and level 4, more difficult, takes more planning, takes more resources, and so not able to do those at as many sites. So I'm going to now go into the results. So from the level 1 visual inspections, 22 of the sites that so I looked at 22 sites, 11 of those sites had partially clogged inlets. So we'd recommend those for maintenance, and just showing some pictures here of a couple of different inlet types. So on the left, we have sheet flow and curb cuts. So any site that had this, the clogged inlets was really not much of a problem, even for the very older sites. And the ones that had issues were ones that were a lot narrower. So the picture on the right, which is only 30 centimeters wide, and you can only really tell that it's clogged because a bit of the inlet grate is broken. You can see how much debris and garbage has built up in there. Another finding from the visual inspection was that some of these had saturated soil conditions. I don't really have any very good pictures of showing the standing water in the system, because it's really hard to see like standing water and mud, like it all looks the same. But this is the most obvious version of it. If you have wetland vegetation, you have saturated soil conditions. So in going out with the plant experts, I also learned some fun things. So most of these are the Typha latifolia. So engineer learning some plant names, yay. So yeah, if you see a lot of cattails in your bioretention cell, most likely saturated soil conditions. And this is more involved maintenance because like, why is this happening? I can't tell from a visual inspection level, and this would involve a little bit more invasive techniques to figure that out. So move on now to the infiltration rate testing. So this was done for 19 sites, and the little GIF on the left is the Guelph permeameter. Looks a bit like a lava lamp, but as the water level goes down and it's taking up the air spaces that are in the soil, and so the air bubbles are coming up, and that's why it looks so fun. The box plot on the right is all of the sites that I looked at. So 5 to 15 measurements for each site. And the colors show the age. So the pinkish one is 3 to 5 years of age, green is 6 to 8 years, and blue is 9+. So recall the design goals were at least minimum, or at least 25 millimeters per hour for an infiltration rate. And all of my sites were above that at the mean and the median. I had one site which was 10 years of age, so they're all on the far right. That was exactly at 25 millimeters per hour at the median. However, my other very old site is much better than that, and also much better than many of the younger sites. So overall, I didn't see a correlation between age and infiltration rate. It would be great if I had more data for the original infiltration rate so I could say this with a little bit more confidence, but I only had 6 sites where I had an infiltration rate that was taken at construction time. And there's the age of those systems there as well. So comparing the infiltration rates that I took to the original ones, again with like a ton of caveats in that I can't ensure that this was done in the exact same way and under the exact same conditions. So caveats there. 5 out of the 6 sites had improved infiltration rates when I did it this past summer, and one of them had slightly decreased. All right, so results for the level 3 synthetic runoff test. So this is dumping a huge amount of water on a bioretention cell and monitoring the water level as it goes down. So I was able to do this at 3 sites with the shown in the graph on the right. And then the sites in blue, oh, and sorry, all of these had under drains. So the sites in blue and orange had drawdown times of 4 and 6 hours. And I didn't see any flow in the under drain. So that means all of that 25 millimeter equivalent of water was absorbed and retained in the bioretention cell. And one site, the one in gray, where the drawdown time was 5 minutes, saw flow in the under drain like fairly immediately. So that's what I've got from the synthetic runoff tests, leading to questions about the one that only has a drawdown time of 5 minutes, but whether it's able to achieve its retention targets. Okay, and the most involved, so this is a site that we've been studying for years at the Courtright Center in Vaughan. So I'm sure other graduate students and other researchers on this call would have seen presentations about this in the past. In this photo, there's a few other students that I've worked on with this, and then I tried to find a good picture of just the bioretention cell, but honestly, we were always studying something on it, and that's why there's always like tons of stuff sticking up in it. So that's what our bioretention cell looks like when it's being like heavily studied by lots of graduate students. In this specific study, we looked at monitoring the inlet and the outlet being from the under drain flow, and we did sampling and flow monitoring. So we have that data for 2013, 2014, which was immediately after it was built. So sort of during its establishment period, and 2017, 2018. So sometime after it's become established. So some more boring box plots to look at, sorry. But on the left is comparing the outlet concentrations during the new period compared to the established period. And then on the right is comparing the inlet and outlet during the 2017, 2018. So it's pretty good at removing total suspended solids. That's stuff we already knew about bioretention, and not so good at removing dissolved solids. So showing that with the total solids there. That's something we knew already. We did see a decrease in the concentration of dissolved solids at the outlet between the new period, 2013-2014, and the established period. So we think that might be indicative of the media having settled out over time. And for nutrients, because I just want to cover this briefly, and this was a much longer study where we looked at nutrients, metals, everything. But briefly, nutrients, we see pretty variable treatment of nutrients across the bioretention literature, and we saw pretty similar things. So for example, nitrogen is reduced between the inlet and the outlet, but that's mostly ammonia because of nitrification, and then we don't see the removal of nitrate, for example. And then for phosphorus, the difference between the inlet and outlet is not statistically significant. However, we did see sort of like a settling out between the new period and the old period. The new period and the established period. So looking at the outlet box plots on the left, total nitrogen had a much higher range or a much larger spread in the data in 2013-2014 at the outlet than in the established monitoring period, where we saw like a much tighter range at the outlet. And that's the same with total phosphorus. So we did see, like overall, it was a lot of removal because of the volume reduction that the bioretention cell is able to do. But in terms of the concentrations at the outlet, pretty steady concentrations that don't necessarily mean treatment of the nitrogen and the phosphorus. So the main conclusions of these studies on mature systems are that the infiltration capacity is maintained over time, and that the actual drawdown times are much less than designed. The infiltration capacity is high, but given that our older site was only 10 years of maturity, we still have questions about whether this maintained will last, so still unsure about when we know when that's failed. So we're clearly over-designing our systems as infiltration beneath these systems is occurring quite quickly. Saw that with the synthetic runoff testing, where 2 of the sites were able to completely absorb the 25 millimeter event and drain and draw that down within 4 to 6 hours. And then from the continuous monitoring, looking at it over a long period of time, the media clearly needs some time to settle before we can really see what its treatment capacity is. So with that, I'd like to thank everyone that helped me with the research, my supervisor, undergraduate research assistants, NSERC, and of course all the in-kind partners who designed and built these sites and let me know about them. And I'll throw it over to Q&A.
Thanks, Sylvie. That was a really great presentation. It's great to see all of your work. So we do have some questions, and I'll remind people in the audience, if you have some questions, please type them in. We're going to take a few minutes for questions for Sylvie. But our first one comes from Job, and it's about the visual inspections. So the question is, how reproducible are the visual inspections? When you do the visual inspections, are there sort of classifications that you use to identify like failure versus non-failure? With that kind of ideas, can that approach that you've been using in your study be used by practitioners to get reliable results?
Yeah, that's a really good question. There's definitely some subjectivity to the way the visual assessments are done. Because someone might, I said partially clogged inlets, like what is partially? So yeah, totally acknowledge that. I think the best thing to do would be to have, like, for specific sites, have specific people doing this over and over again. So develop your own protocol in-house and repeat that and train new people in the same thing, so that you're identifying it in the same way or compared to a same benchmark. And I think photos would go a long way to like helping that process as well. That's for describing things like, however, the visual assessment is fairly basic as well. So just looking at how the inlets and outlets are doing and how if it's saturated or not. If you're going to do a little bit more involved visual assessments, so like checking the plant cover change over time, then you would need, of course, like a little bit more expertise on plant communities. And so you also want to like have those people in place with that expertise. Yeah.
Yeah. So my next question is about the really interesting results that you showed with the drawdown time. You know, as you started, you saying, you know, these systems are intended to drain water over 24 or 48 hours, but you're seeing, you know, from your cases, 4 or 6 hours, in one case, immediate short circuiting to underdrain. But if we assume or agree that these systems are over designed, what do you recommend needs to change in the design practice? Like, what are we doing that is forcing this like over assumption or excessive conservativeness? What do we need to change in terms of how we design these systems?
Yeah. I get where it comes from. Like, engineers are always applying a safety factor, and we want to make sure that these systems work over the long term. And we assume that they'll clog over time. And so we're like, okay, let's add in some safety factors that account for that clogging. Then we're seeing that in the natural system that like maybe it's not clogging as quickly, or maybe it's able to like maintain itself and prevent that clogging. One thing in Ontario specifically, we have a safety factor on the bottom infiltration rate, where it's, what is it, divided by 2 or multiplied by 2? Anyways, it ends up being like a lot lower than what you measure in the field. And so underdrains often get put in and then are not closed or not monitored. And so if your soils are on sort of the cusp of that tight to not tight range, maybe like a silty clay, then everyone's like, yeah, underdrain. But we've seen from other like jurisdictions, so Minnesota had similar issues where they're putting underdrains in everywhere, not getting much retention. Then they've implemented a design change of like, we're going to put underdrains with closed valves on and only open the valve if it's if we're seeing ponded water. That's a pretty simple solution for having an in-between between an underdrain and not an underdrain. So that would be my recommendation, I guess, is like you don't always need an underdrain, and like, let's think of some ways to, yeah, sorry, I'll stop talking. Go ahead, Jen.
Good. You know what? And I think that's, I think you're kind of highlighting things that's going to connect very well to Tamara's presentation later, because I think what you're saying is maybe one way we could deal with this is by making these systems more adaptive. So that they can be conservative, but we can actually force the functions that we want when we want them. We're going to do one last question before we move on. So this question comes from Albert. Was there a difference in the reduction for dissolved and particulate phosphorus from your heavily studied bioretention cells?
So we don't have that separated out, the dissolved and the particulate. We do have separated out total and the orthophosphate. And for the total and the orthophosphate, both were not significantly reduced between the inlet and outlet.